Hello dear students, what I'm trying to do in this quick tutorial video is just to give you a quick recap on how you can work the design for the straight L stub, matching stub, and the reverse L matching stub. So a reminder for the straight L situation, here is what you have. So basically you have a load impedance or a certain given impedance that you want to expose to matching, and then the circuit which is doing the matching is composed of a transmission line, and then at the end of that transmission line we have another parallel line which is introducing the parallel impedance, and that parallel line can be either an open circuit or a short circuit as discussed in the lecture. Okay, and the components of this are we have ZL, we have an impedance that you see from here, total impedance, which is the desired matched impedance. So this is known to you and this is known to you. So you know initially what was the initial impedance that you start with and what's the desired impedance. And some intermediate values that we have are the impedance that you see at this part, let's call it ZA, and the parallel impedance itself ZP, and that one was a pure imaginary, so it's composed of X, J. So it has some value, but it's a pure imaginary impedance, right? And then because of this setup, remember that we have parallel connections and so on, so we work everything using the normalized admittances. So so basically the equations that we can write, we are going to write them in terms of the normalized admittances. So basically the equation that we can say here is for Z, we have ZD, we have the corresponding admittance, call it YD, and for the ZL we have YL, and for ZA we have the corresponding admittance YA, and for ZP we have the corresponding admittance YP, right, Y parallel. So the equations that we can write in terms of those admittances is that the desired impedance YD is equal to, right, the parallel admittance Y P plus the admittance that we see from here, the one that we see from this point, so this and this, the one that we see from here, and ZP, they get connected in parallel to give us ZD, right? So in terms of admittances, this is gonna be YA, right? Now since we know that YP is pure imaginary, so we can write this as YD is equal to some pure imaginary value, okay, plus the YA. Now YA is a general admittance that can have a real and an imaginary value. Now from this equation we can figure out that YD and YA, the desired and the admittance that we see from the end of the transmission line that we use for the matching, we know that both of these will have the same real value, right? So this, and since I already know the real value here because I know the desired impedance that I want to achieve, so I know the desired admittance, then this real value is known to me. I can get it from YD. So if I go now for my Smith chart, right, I have one locus, which is basically a real value coming from YD. right? The other locus that I have is that both ZA and ZL belong to the same transmission line. So I start here by ZL and I move across the transmission line until I get ZA. This is before connecting the parallel part, right? So both these ZL and ZA belong to the same circle centered around the origin because they correspond to movement on a single transmission line, right? So this means that if I know ZL, I'm going to simply plot ZL wherever it belongs, right? So let's say, for example, my ZL belongs to this point. Okay, so this is my YL now. So we are dealing with the normalized values, okay? So this is my YL, the normalized admittance, okay? Now, my ZA will belong to the same circuit that YL belongs to, right? Because both of them come from the same transmission line. So simply I can plot this other circle coming from the movement over the transmission line, right? Which will have YA somewhere, but for sure it has YL, right? So this YL allows me to know how to draw the circuit, while knowing the desired impedance gave me the real part that allowed me to plot this other circle. Now the intersection of those two circles, okay, is gonna give me the solution. Remember that the solution that I will get from here is the normalized A, so call it YA1 and YA2, okay? Now, knowing YA, I can move on and design ZP or YP such that I get the desired impedance. So now if I know the YA, I can simply figure out what should be the impedance that I see from here, which is basically YP, right? So YP or ZP is the impedance seen from here only for the parallel part, right? So now I can let's see how the situation is going to be very similar but slightly different for the case of the reversal. So now, just out of completeness, the remaining part is basically to figure out what's YP, and I know that basically I was saying that now we know that YD is equal to YP plus YA, right? And this is known to me from the solution over the Smith chart. This is known to me because I know what's the matching outcome that I want to get out of this circuit, and this is the only unknown part, so I can easily figure out what's the required value for this parallel impedance, and then I can design the transmission line, again, assuming short circuit or open circuit, as we did in the lecture. So that becomes a straightforward. Now let's look at what happens in the case of the reverse L. Okay. Again, following the same principles, we have a load impedance, ZL, and its corresponding admittance, YL. That impedance is connected to matching circuit, which is composed of, again, transmission line, right, and parallel guy. But that parallel guy is now being put at the start rather than being at the end, right? So again, similar to the previous situation. In this case, what I see from here is just the outcome that I am looking for. So this becomes my Z desired and its corresponding admittance Y desired, right? And then I have only for the parallel part. So what I'm doing here is only for the parallel part without being connected to the red line and without being connected to the load. So that parallel part by itself, the blue one only, disconnected from everything, will have an impedance called Z parallel, and its corresponding part is going to be Y parallel, which is equal to J somebody. So it's pure imaginary again. So in addition to those impedances that we see there, we also define, um, let me just keep this as our final target. So keep it in black. So what impedance that I see from here, okay, which is basically the equivalent of the parallel connection of the load and that blue line, let's call that impedance um, something like ZL dash, and then its corresponding part is going to be YL dash. So this is right after connecting the parallel with um, the load without actually doing anything on the red transmission line. So the equivalent of those two connections together. So now the equations that I will have, um, I will actually put this in, I'll keep it as it is. Okay. So now the equation that we will have in this case is that, and again we work on admittances, so that Y, sorry, let's keep it in black color, so that Y L dash, the equivalent of both of them, is equal to YL, which is known to me, the load impedance, plus the parallel impedance represented as admittance, right? So plus YP, right? Um, Now again, this says that YL dash is equal to YL, right, which is known, plus some pure imaginary part, right? So now I know that YL, which is known to me, and YL dash, which is unknown to me, they both share um, the same um, um, real value, right? So that gives me a locus for that real value, which is actually coming from knowing the load, right? So I have one circle here, again going to the Smith chart, right? I have one circle that represents the real value of that location for the real value of that YL dash, which is exactly the real value of my load. That's why I draw the circle in uh, black, because the value comes from the value that I know from the load itself, right? Now, in addition to that, um, I know that my ZL dash, right, uh, right, the one that I see right after that point, the one that I see here, which is the equivalent of these together, the load and the parallel, as well as the desired, which is known to me, right? They share the same transmission line, right? So I start here by ZL dash, and I move across the transmission line until I get the desired, which is known to me. So now if I know the desired impedance, I'm going to simply plot the location. Let's say uh, this is this is the location, for example, of my desired admittance normalized, right? So this is my YD, okay? Then I know that circle centered at the origin, which contains this YD, right? It's gonna be a locus for my, right? So I know that this circle is that includes YD already, is a locus for my unknown ZL dash, right? So it's a location for this ZL dash, or basically the normalized version of the admittance, because we are dealing with admittances, right? So now I can get 2 points out of this point and this point, and both of these are possible values for the normalized version of that YL dash. We call it YL dash 1 and YL dash 2, right? So now I know the equivalent here, right? Immediately from this, I know the relation that YL dash, right, is equal to Y of the load plus Y parallel. This is already known to me because I get it from the Smith chart. Is already given in the problem, so known to me from the start, and then I can figure out the parallel. Now, after figuring out the parallel impedance, right, um, I can now figured out already all my design, right, because I already got the location of the desire, got the starting location, which is this point that I start from. So basically, um, this distance, um, starting from here and moving this distance for the first solution, for starting from here and moving this distance for the second solution, is gonna give me the length of the red transmission line, right? And that means that I've designed this one, and for this equation, I figured out this one. And again, after figuring out the parallel value, I can go assume short circuit, open circuit, and figure out the length of this transmission line, right? So I hope this clarifies how you can approach the reverse L for your project, as well as for the first part of your assignment 4. I'm going to post a new deadline where you can submit only the first question of assignment 4 to be marked separately later on. Thank you.